going to do an early stream this morning. This is Sunday, September 3rd. So it was supposed to be the stream of Wednesday last week. It's just Twitch went down and we couldn't do it. So we're going to jump up into here this week. You can't see half my head. That's wonderful. There we go. Okay. It's for the CP Physics class, week 2 of these kind of online streams. We've just gone through this past week on how to do a lot of like our old algebra skills that we might have been rusty on, and a little bit of metric prefix conversion and unit conversion. So that's what we're going to look at today. We're going to look at a lot of algebra skills and just some stuff that you might have forgotten. I posted on our Google Classroom a little bit ago some problems for the homework, and what we're going to do is we're going to look at a similar problem with a slight difference here. So what we're going to do is we're going to look actually at this problem. This was the boiling point problem that everybody loved in class. I say that sarcastically, right? Because nobody liked this problem because we had an issue where a lot of people were putting in the pressure, which is P. They were putting that value of 50 in here instead of up here in the actual variable for these cube roots, because the units would cancel and you'd get that. We're going to go through this problem and the force problem beneath it, just the other way around, slightly easier method. What you would get whenever you have this quantity at the end, you actually have your determinant variable and you're looking for something on the inside. How we'll just have to rearrange this equation, work it out, and get our final answer. So this and this electrostatic field equation are the two problems we're going to be working at today, just kind of going through them a little bit backwards, where we have the value that's already isolated and we need to pull out this sucker on the inside. Okay, so that's what we're going to be doing here. To give us an idea, it's we're going to start at the top and move to the bottom. Okay, so looking at the first problem, some experiment was performed to determine how the boiling point of water is affected by the air pressure. And the equation we have there is that B, the boiling point, equals 19.7, and these are the units here. So I'm going to put the units in green so that we don't get those confused. Degrees C by the cube root of kilopascals times the cube root of the pressure. Now, just a little side tangent. I mentioned this in class, but if you forget, you can state that things like the cube root of a variable x, that's equal to raising it to a fractional power. So it'd be like the 1/3 power. This quantity out here is actually the quantity just placed in the denominator. So if you wanted to, you could actually have something weird like, what is the 7th root of x cubed? And that would be equal to x cubed, because the x to the cube, over 7. So it's like x to the 3/7. That's a little easier way to write that. I like this for whenever you get like really weird stuff, whenever you're going to college and whatnot. This is a lot faster to write, but if you're still used to writing it with the whole radical and everything, that's where we're going to be right now, just because that's kind of what you're used to. Okay. And what we have in this problem is that this boiling point right here, we know that is 60 degrees Celsius. Okay, so what we can do here is we can just plop in a value. So what we'll have is 60 degrees C equals the quantity 19.7, oops, I guess do this in green still, degrees C over the cube root of kPa times the cube root of P. Okay. And so we are solving for this cube root of P here. This is the actual variable we're looking for. So we need to find out what that is. So what we're going to do first is we're going to isolate that variable. We're going to take this quantity here. We need to move it out. Now, since there's technically, and it's implied, a multiplication sign here, these are multiplied together, we're going to have to divide out this 19.7. So what I'm going to do here is I'm going to divide by 19.7 degrees C per the cube root of kilopascals. When I divide like this, my units actually cancel out here, which is nice, along with the number. And then when I divide on the other side, it's really stuffed in there. It's actually going to happen is that my degree C are going to cancel out, and I'm actually going to have a number here in the cube root of kilopascals. And if you don't see how that works, if you think back to your math classes again, and we'll kind of do a tangent over here. Tangent. If you think back to your math classes, if you have a number like 1 over 2/3, this is really equal to 3/2. Because if you remember, whenever we divide by a fraction, we take the reciprocal of it, so we flip it, and it will become 3/2 like that. So when we're dividing down here, what we actually have is that the degrees C are being multiplied by the reciprocal of the fraction, so by the cube root of kPa, and divided by the degree C. So the degree C end up canceling out, and this is the unit we get. So that's helpful. If you do this division, I'm not going to run that for you. Use your calculator, but if you want to give yourself a quick check, this number in the bottom, it's about 20. 60 divided by 20, that's about 3. And I did that real quick just by saying, hey look, 60 divided by 20, my zeros are going to cancel each other out. This is a common little trick whenever you have two zeros as you're going through problems or you're dividing by zeros. That 0 and that 0 are just going to wipe each other. Everything's going to get scaled down by a factor of 10. And I know what 6 divided by 2 is. You do too. That's just 3. So over here, it's going to be a little bit more than 3, but I'm just going to put 3. The units of this are the cube root of kilopascals, and that is equal to the cube root of some pressure. And this is what we're still looking to find. We're still looking to find that pressure. Now, a little bit of a math background here in case you've forgotten. If you would like to get rid of a radical sign, if we kind of think back up to what we did here, well, if this cube root of pressure is really like the pressure to the 1/3, then if I could get this fraction in the exponent to be 1, then it would just be the pressure that's left. So I need to get that to say like 3/3. Well, to do that, I simply need to raise this quantity to the 3rd power, because that would be equal to saying like pressure cubed to the cube root, that equals 1, so it's just the pressure. And then since I've cubed it on this side, I need to cube it on this side. When I do that, I need to make sure I cube the 3, and I'm going to cube this unit here. So 3 to the cube, well, that's 3 times 3, which is 9. 9 times 3 is 27, so I'm going to get 27, or approximately, because remember there was a decimal here somewhere. Our unit here is no longer the cube root of kPa because we've done this to both quantities. This is actually just kPa, kilopascals, and that equals our pressure. And we're done. That's it. That's the problem. Okay? So there's one math move, dividing underneath, and then cubing a quantity in order to get that there. Okay, and a little bit of a math background over here in case you've forgotten some stuff. So nothing too crazy there. Hopefully you remembered that. Hopefully that wasn't something that you needed help with. The biggest things here are watching your units and watching where your units go, and just remembering some little math tricks that you've done in the past. Okay? Okay, we're going to take a look at another problem then. The second problem we got here is this electrostatic force problem. We're not going to deal with electrostatic forces in this class, but it's a nice, easy equation. If you're here from the AP class, maybe that equation looks familiar to you because we have been doing electrostatics recently. So we're going to look at this here. Force equals 0.427 newtons centimeter squared divided by some distance squared, and we're using d here for distance, but commonly this is actually r. We're going to calculate the distance when the force is at 5 newtons. So that's what we're going to be checking out here. to do this, and I'll just rewrite the problem in a straight line if I could ever draw one. What problem we have is f equals, and then I like to put quantities because I'm paranoid about numbers, newtons centimeters squared, all divided by some distance squared. Now what we're solving for in this problem is the distance. That's what we want, because we're given in the very beginning, just like last time, the force. We're given that quantity. We know in this problem that the force is equal to 5 newtons, or 5.00 newtons if you're trying to keep track of sig figs, and that would be equal to our 0.427 newtons centimeters squared divided by the distance squared. Now, an issue I often see students do in this problem is, in order to get this distance by itself, students will often divide by the 0.427. And if we look at that, this is the wrong way to do it. It's not the wrong way, but it's the long way. If you do that, if you say, let's divide, then you're going to get 5 divided by 4.27 newtons centimeters squared, and there's newtons up here, equals 1 over d squared. But this d's in the denominator, it's stuck there. I don't want that. If I did accidentally do this, what you can actually do is you can pull a reciprocal to each side, and you can only do this because it's a full multiplication division. You can swap the tops and bottoms and call it a day. You see, you kind of have to do that because these newtons are going to cancel out, and your centimeters are down below anyways, and you actually want a distance. You don't want 1 over a distance. So this isn't super helpful. What we need instead is we need 0.427 over 5 equals d squared, and that's what the flip would be. We could either see that we messed it up when we needed to run a flip, or what we can do coming back down to here is we could just do it kind of the more logical way. I need to get this d squared out of the denominator, so what I'm going to do is I'm going to multiply each side by d squared. Now that I have that, this would read d squared times 5 newtons equals 0.427 newtons centimeters squared. Now I can just go and divide by the 5 newtons here. When I divide by the 5 newtons, they wipe. Over here, 5 newtons. My newtons wipe, which are good. And I get a very small number here. If we work out what that number is, if this was 1/5, that'd be like 0.2. And this is a little under half of 1, because it's like 0.4. So it's a little under half of 0.2. So it's approximately 0.1. If you have a calculator, you could work that out. I'm going to let you have fun with that. But essentially, we've got d squared equaling, and I'll put a little tilde here, it's about 0.1 centimeters squared. Now the issue here is we are looking for d, and what we're stuck with is d squared. And note our units here match up, they're centimeters squared. So the simple solution to that is, let's take the square root of everything. If we take the square root of both sides, what we're going to find is d. When we take the square root of 0.1, we're going to find our answer. When we take the square root of centimeters squared, we're going to get a quantity in centimeters. Okay, so that's what we'll have right there. And then you're done. That's that. That's how we can work out this problem. It's very similar to the problem above it, when we were talking about pressure and how we kind of had to move some stuff around. In this case, we had to move some stuff around as well in order to find those values. Okay, so hopefully that wasn't anything too crazy for you. Something that you hopefully had seen before in your math classes. Just a little bit of a refresher for you as you're doing that. If you find that you're struggling with any of this stuff, just come and talk to me, or find me throughout the day, or check out these videos and see what's going on there. More than happy to always help. Okay, we're gonna go down for a second here for the AP class to jump on so they can look at some stuff.